Welcome to CATS Tutorials, and in this video I'll be covering practice problem 8.5. If you haven't subscribed to my channel, please subscribe, and if you like this video, just go ahead and give it a thumbs up. So we're given a parallel, so this is a source-free parallel RLC circuit, and we're given the values of all of the components as well as the initial conditions, so we don't have to find the initial conditions. Then we are asked to find v of t for time greater than 0, right? So let's do that. So first start by looking at the type of response which we have here. So we're going to first start with the damping factor, which for a parallel RLC is equals to 1 divided by 2RC. And we're going to find the resonant frequency, or the undamped frequency, in radians per second, which is found by this formula. Substituting all our values, so substituting 1 divided by 2RC, so R and C over there, you're going to find a damping factor of 10 amperes per second. And here, just substituting 1 divided by the square root of L multiplied by the square root of L multiplied by C is going to give you this resonant frequency of 10 radians per second. So you'll notice that your damping factor is equals to your resonant frequency. And this tells us that the type of response is a critically damped response. And the general formula for a critically damped response is V of t is equals to A1 plus A2 multiplied by T multiplied by E to the minus alpha T, right? So we have this one initial condition, which is going to help us to find the coefficients, and we are going to find the other initial value, or the other initial condition, which is going to help us, which is basically dV divided by dt. So doing that, looking at the top node over here, we're going to say V divided by R plus the inductor current, which is IO, so plus IO, which is the inductor current which you have over there. Then we're going to finally add the capacitor current, which is essentially C dV divided by dt equals to 0. So we're given this as 50 milliamperes. So let's just rearrange all of this so it makes sense, or it looks good. So dV over dt is equals to, so taking these two to the other side of the equal sign, we are basically going to have both of these on the other side. So it's negative V divided by R plus IO. Divide all of that by C. So substituting the values which you know, or the values which you have for time at 0, time 0. So dV over dt at 0 is equals to, so the value here at 0 is 0 as given to us in the question. So that is 0. That is just 0. So negative 0 plus, and IO is 50 milliamperes as given to us in the question. So 50 milliamperes. Then we're going to divide all of that by, so we're going to divide 50 milliamperes by, so negative 50 milliamperes divided by C, which is given to us as 25 milliamperes. So the milli is going to cancel out, and we only are left with 50 divided by 25, which is actually 2, right? So the value of that should be 2. dV over dt at a value of, at point 0 is 2, not forgetting the negative sign. And therefore we're going to have dV over dt times 0 is equal to negative 2 volts per second. We now have two initial conditions, and we're going to use them to find the coefficients of this response, which is going to be our answer. So at V of 0, we know that that is 0. And we're going to substitute 0 wherever we see t. So that's going to be 0, that's going to be 1. So we have A1 is equal to 0, right? So A1 is 0 from that basic calculation which we first made at that point, right? So A1 is equal to 0, because substituting 0 wherever we see t will only leave A1 exposed, right? So that is all we have in terms of A1, and we're going to proceed to find A2. So dV over dt is equals to the derivative of this. This is assumed to be constant, so it's going to be 0. The derivative of that is going to be a2 multiplied by e to that. And then we leave this as it is. Then we're going to differentiate this. It's going to be negative that. Plugging in the actual values and looking at this at time 0, we know that at time 0, this is negative 2. So we're going to equate all of this to negative 2. Substituting 0 over here, we're going to have a2. Then here, this is 0. This is a value which we found before. a1 is 0. And there we're going to have negative this. So the damping factor we found to be 10. So negative 10 multiplied by a2. That is going to be 1. It's equals to minus 2. So this is what we basically have with us over here. And so after doing this, after finding the derivative of this, let's see what we actually have. So the derivative of this, let me just see if I computed the derivative correctly. So that's going to be 0. That's going to be a2. That's going to be multiplied by that. This is 0. That's going to be 0. This here is going to be 0 as well, because it's multiplied by t and we aren't actually doing anything. So this is wrong. After substituting our 0 over here, we're going to have a2. Substituting 0 there, this is already 0 as we previously found. So all of this is 0 multiplied by that. So this is what we basically have. We only have a2 equals to the value of dv over dt at time 0, which is negative 2. So now I have both coefficients, and we're going to conclude by substituting the coefficients into the general formula over here. So our final answer for v of t is equals to a1, which is 0, so 0. Then we have a2, which we found to be negative 2 t, and our damping factor is 10, so that is what we substitute. And therefore, v of t is equals to negative 2t e to the minus 10t volts for time greater than 0.